In this lesson, we're going to look a little bit at gyroscopic motion. Now, to be fair, gyroscopic motion can be very involved mathematically, takes much more discussion than what we can do here on this single page of notes, but it's such an important concept. It's used in compasses, aircraft, inertial navigation systems for satellites and missiles and helicopters, and now they even have what are called MEMS gyroscopes, micro electromechanical systems gyroscopes that they put into electronic devices, along with detectors that are called accelerometers to measure the acceleration, that allow very sensitive direction and motion sensing. So it's a very important concept. Now, one of the most important things in terms of beginning to understand how gyroscopes work is to keep in mind this very first statement. Understanding what a gyroscope does is all about tracking what the angular momentum vector of the gyroscope is doing. So we are going to look at the gyroscope, and I want you to constantly focus on the angular momentum vector and how it's changing, because it really is, as it says here, it's all about the delta L. How is the delta L changing? Well, what is a gyroscope? Here we have a schematic of a gyroscope, and it consists of a big, sturdy, heavy wheel called the flywheel. So that's the flywheel of the gyroscope. And that needs to be set spinning. So the flywheel has some external torque, some external force act on it to get it spinning. So that spinning results in an angular momentum vector, and remember we have to track what the angular momentum vector is doing. An angular momentum vector L due to that spin, and that is called the spin angular momentum. Now, gyroscopes have a very startling behavior when you first see them, because they seem to defy gravity. The center of mass of this big heavy wheel is right at the center, and yes, gravity does not disappear, it is pulling straight down. So ultimately we want to understand why it is that the flywheel just doesn't flop over and fall to the ground, and clearly forces here at the pivot are going to be important, right? Because we do need to have a way that it is supported and gravity just doesn't pull the whole thing and move it in the y direction. But we're first going to concern ourselves with the other startling behavior, if you've never seen them operate, in that the flywheel will not only have the spinning velocity omega that is shown here, it is going to have what is called a precession velocity, meaning that gyroscopes also move and precess around this vertical axis. Now, why does that occur? So let's start there. Why does that occur? Well, we're going to start mathematically with Newton's second law for rotation, torque equals dl dt. And our torque is the torque generated by gravity, so it's R cross mv, where R is from the vector from the pivot point to where the force acts at the center of mass, mg. So we're replacing R with A because we don't want to confuse it with the R of the flywheel. So that'll be the precessional R, the motion. So we have R cross mg, and we get sine of 90 degrees between R and mg. So we get A mg equals dl dt, and that is going to be our very important first equation 1. Well, how is dl dt changing? Well, torque is what's changing it. So the torque vector, when we do R cross mg, so take a moment, pause the video if you have to do your r. All right, here's your r vector. That's your r. Now it's getting a little sloppy here. That's the r vector cross mg. All right, well, let's get the red mg in there. Mg gives us our torque. Well, let's get that blue. Gives us our torque, r cross mg, in this direction. So that is the direction, right? The torque and the dl have to have the same direction. So the torque is causing this dl. So there's the dl in the same direction as the torque. So the L, the spin angular momentum vector L here, gets pulled in this direction, and when it gets pulled in that direction, it pulls the flywheel and the axle, and there we get our precessional motion around this z-axis. Well, the equation that describes that motion is really very, very simple to get to when we consider what is happening at over any small increment of time. How is the angular momentum dl changing in a small amount of time? Well, in a small amount of time, that dl is going to sweep out a very small angle, d phi. Now that d phi will go with the precession, not the spinning. So that d phi is going to be very small, and we know in general for very small angles theta is approximately equal to sine theta, approximately equals tangent theta, and for us, tangent theta opposite on hypotenuse is going to be opposite dl hypotenuse h. So the triangle we're looking at here is roughly a right triangle for very small increments. We have our opposite on hypotenuse. Our opposite on hypotenuse equals our d theta, and we are going to substitute dl in for dl up here, and voila, we have our equation, because we get amg equals L d phi dt, and d phi dt is our capital omega. So our capital omega is still an omega, so it's a velocity, but capital omega is going to be our precessional angular speed or angular velocity. And notice that when we look at the equation in terms of L equals I omega, whoops, let's do that in red. L equals I omega, we get a very interesting result. We see that as the spin of the gyroscope slows down, so as omega gets smaller, it's on the bottom of that fraction. So as it gets smaller, the precession angular speed actually gets bigger. And now we can understand the motion of a top and see how we are defying gravity here, or how the top defies gravity a little bit. Why doesn't it just flop over? Why doesn't that center of mass, when it gets pushed, if this top was spinning just on the z-axis, why is it that that center of mass doesn't flop over? Well, not only doesn't it flop over, we'll see a nice video that it actually gets pulled back up. The center of mass goes back to the z-axis, and the L vector goes back to parallel to where it was. So, and that, believe it or not, we're not going to go into detail here in this lesson, requires friction on the ground to allow that push back up to the top. But we can understand just from circular motion that as that precessional speed increases, the centripetal force is also then going to increase. And that we can think of that centripetal force necessary pulling in towards the center is kind of what's pulling it back to its upright position And again, we'll talk a little bit more about why it is that friction at the base is necessary. But we definitely wanted to get our equation for precession and understand this boxed equation here a little better, because we had all the physics to understand that in place, and now we know a little bit better about the mathematics behind how a gyroscope or a top behave.